So in this lecture, I will discuss the two-dimensional Ising model at high temperature. The theorem we would like to prove reads as follows. So there exists a beta 1 such that for all beta less than beta 1, so for high temperatures, the limit as n tends to infinity of the expectation of the spin, the value of the spin at the origin under the measure on the box of size n at temperature, inverse temperature beta with positive boundary conditions, that this is equal to 0. So this is the theorem, and well, since this expectation is converging to 0, and sigma 0 takes only -1 value and +1 values, this tells you that the probability that the spin at 0 is equal to -1 tends to 1/2 as n tends to infinity with positive boundary conditions, which means that the origin does not feel the influence of the boundary if beta is small or if the temperature is high. So this is the content of this lecture. And we will prove that in 2 steps. First, we will prove that for all n, this expectation, so sigma 0 n beta plus it's non-negative, well, the fact that you have plus boundary conditions gives a higher probability of the spin to be +1 than -1. And for this reason, this expectation will be non-negative. And then the second step will be to prove that the limit as n tends to infinity, say the limit sup of this quantity, sigma 0 plus n beta, that this is less or equal to 0, provided beta is sufficiently small. So in the first part of the lecture, I will prove this inequality, which is the difficult part in the proof of this theorem, and then I will show that this inequality holds at the end. So the first part of the proof of this inequality will be to find an expression for exponential minus beta h plus n of sigma. So we will write the energy, the Hamiltonian, in a special form which will be very useful in order to prove that inequality. So let me remind you that the energy with positive boundary conditions of a configuration sigma, it's equal to minus all bounds x, y in En of sigma x, sigma y, but here I will require these 2 points to be inside lambda n, and then we have the contribution of the boundary. So here we have, let's say, x in lambda n, y outside lambda n, and xy a bond of En of sigma x eta y, where eta is the configuration which is identically equal to 1, so eta y it's equal to 1 for all y in Z2. But we adopted a convention in the previous lecture in order to have a very simple form of this Hamiltonian. We adopted the following convention. We said that sigma x will be equal to 1 for all x which does not belong to lambda n. With this convention, I can just replace eta y by sigma y and then rewrite this energy in a very simple form, which is minus all xy, all bonds or edges in En of sigma x, sigma y. So I don't have to distinguish the bonds or the edges which are inner edges or which are contained, which both vertices contained in lambda n from the other ones. We can put them all inside this expression. So this is a formula we have seen for the energy when you have plus boundary conditions. And remember, En represent the set of edges which touch lambda n. Now, I want to present a very simple formula. So what I claim is that beta times sigma x, sigma y can be written in the following way. I can write this as the hyperbolic cosinus of beta plus sigma x, sigma y times the hyperbolic sinus of beta. So that's very easy to check because the product sigma x, sigma y can take only two values. If it takes the value plus 1, we have on the left-hand side exponential beta, and here you have cosinus hyperbolic of beta plus hyperbolic sinus of beta, and the sum it's equal indeed to exponential beta, while if the product is equal to minus 1, on the left-hand side you have exponential minus beta. So here you have a minus 1, so the exponential beta which appears from the hyperbolic cosine will cancel with the exponential beta appearing from the hyperbolic sinus, and you get only the exponentials minus beta on both sides with the plus, which will give you, since both are divided by 2, you will get that indeed the left-hand side is equal to the right-hand side. So keep in mind this identity, and remember that what appears are the weights, and the weights are given by exponential minus beta times the energy of the configuration. So these are the weights which appear in the Gibbs measure. Now, I can just replace the energy by this sum. So you mind that the minus sign will cancel, so that this will be equal to exponential beta times the sum for all xy in En sigma x, sigma y. And, well, I can write this as the product of xy in En of exponential beta sigma x, sigma y. And now I can use this identity, but on the right-hand side, I will divide that by the cosinus, the hyperbolic cosinus of beta, and multiply that. So that will be, by doing that, what I get is that this is the product for xy in En. So I have now the cosinus, the hyperbolic cosinus of beta. And then when I divide that by the hyperbolic cosinus, what I get is 1 plus sigma xy times the hyperbolic tangent of beta. So this is the expression for the weight, and mind that since this is a constant, I can still rewrite this expression as the hyperbolic cosinus of beta to the power lambda n, and here I have the product of all xy in En of 1 plus sigma x, sigma y times the hyperbolic tangent of beta. So here is an expression for the weight. And by using this expression, we will obtain a formula for the normalizing constants z in the next take. Mind that I just observed that there is a mistake here. I wrote lambda n, but actually I meant En, right? We have this constant, which appears one time at each bond. So at the end, what I get is that this is the hyperbolic cosinus of beta at the power En, when remember that I'm representing by modulus of En the number of edges in En. So this is the formula we obtained. I'm not yet finished. Now I want to use the following identity. Suppose that I have a finite set A, and I have a product of z in A of 1 plus f of z. This looks very similar to what I have here. here, note that instead of writing hyperbolic tangent, I just wrote th of beta. So we have a similar expression here, and what I want, the point I want to make is that we have the following identity. This product can be written as a sum over all subsets B of A of the product for Z in B of Fz. Mind that here I'm taking the empty set, so B can be the empty set, in which case I have here 1. And so you can prove this identity by induction. You see that if A has only one element, then we have on the left-hand side 1 plus Fz, and this is exactly what appears here. If you take B to be the empty side, this is 1. If you take B equal to the point Z, this is Fz. So this is true if A has one element, and then if A has n plus 1 element, well, you just use this formula for the n elements, and this is multiplying 1 plus Fy. 1 will give you all the subsets B of A which do not contain Y, and Fy times this expression will give you the sum of all subsets B which contain Y. So in this way, you can prove this identity, and I leave as an exercise to you the details of this proof. So I want to apply this identity to that expression. So let me forget for one moment this factor and just rewrite that what we have here is the sum of the product over all edges in En of 1 plus sigma x sigma y times the hyperbolic tangent of beta. So by this identity, this expression, it's equal to, now we have all subsets of En here. So all I will represent by A the subsets of En. And we have a product over all edges in A of sigma x, sigma y times the hyperbolic tangent of beta. So this product, it's actually equal to that sum. You see that here, this factor appears once for every term. So what we get here is that if you take it out from the product, it's that this is the hyperbolic tangent of beta to the power number of elements. So this is equal to the same sum, A in En, then the hyperbolic tangent of beta to the power of the number of elements of A, and then I have x, the product xy of sigma x in A, sigma x, sigma y. Fine. Now I want to write a formula for this product. So you see, you have A is a subset of edges. So let me write a subset of edges quickly here. So let's say that A represents this number of subsets of edges. So I need to introduce some notation. By V of A, I will represent the set of vertices which belong to one edge in A. So these are all x in Z2, such that there exists a y in Z2, and xy belongs to A. So in this example, well, VA will be the subset of Z2 made by the union of all these vertices, of all vertices of an edge in A. So this is the set VA. And then once you fix a vertex, I will say that a vertex in A, well, maybe this terminology is not very good. What I mean is that a point which is an endpoint of an edge in A. So a vertex in A means a point in Z2, which is an endpoint of an edge in A. So these are inbred these endpoints, these vertices, the elements of VA. And now, once I fix an element in VA, I just define the degree or the index, the incidence index in A of this point, which will be, well, the number of edges whose Z, it's an endpoint. So the incidence index, dA of a point Z, will be just the number of elements, so the number of y's in Z2, such that yz belongs to A. So let's see, for this point here, we have, so the incidence index, or the degree of this vertex is 1. It's 1 also for this one. For this one, it's 1. 1, 3, 1, 2, 1, 1. But I can extend this definition for all, not only for the elements of VA, but all the elements of Z2 by saying, for instance, that the degree of this element, it's 0. So now dA of Z, it's defined in Z2. So you take a point in Z2 and you see, well, how many edges which belongs to A have this point, so Z, as a vertex. So you fix Z and you check how many edges in A use Z as an endpoint, has Z as an endpoint. So this is new definitions and notations, and just to well, so that we can simplify this expression. My first point here is that, well, note that if this edge, okay, so what I don't want to erase maybe the last one. So my point here is that once this product with this notation, I can just rewrite this as a product over all Z in, say, Z2 for the moment, or maybe let me write that as lambda n union gradient of lambda n. So if you have an edge in A is a subset of En, so the vertices of this edge belong either to lambda n or to the boundary of lambda n. And with that, we have sigma z, which will appear, and at which power? Well, it will depend on the number of edges which uses z as a vertex, and this is exactly what I defined as dAz. So I can rewrite the sum as a sum over all subsets A of En, the hyperbolic tangent of beta to the power A, and then now I have a product of all z in lambda n union the gradient, the boundary of lambda n of sigma z to the power dAz. Where mind that this can be 0. So if in this example, and if this point here belongs to lambda n, what will appear here is that we have sigma z, so the spin which is either equal to +1 or -1 at z, at the power 0, which is 1. So there is no harm by introducing edges or vertices which are not used by A. So this is a first remark, and now what I say, it's by our convention, if z does not belong to lambda n, then sigma z, it's 1, and 1 to any power will be equal to 1. So I can just forget about these vertices which are not in lambda n and rewrite this expression as the hyperbolic tangent beta to the power a. And here I have the product of z in lambda n sigma z to the power dA of z. And so now if I want exponential minus beta, what we proved up to now, it's that this weight, it's equal to this factor, the hyperbolic cosinus of beta at the power en, times this sum. So this is what we proved so far. So this is the formula we obtained, and this is the end of step 1. So in step 1, we obtained an equation for the weight. So the weight is given by this expression. Now I want to use this expression in order to compute the partition function, to get a formula for the partition function. So remember the partition function, Zn plus beta is just the sum over all configurations in omega n of the weights exponential minus beta h plus n of sigma. So this is the partition function. Now I replace this expression by what appears here, and I will just invert the order of summations. So this will be equal, I have the hyperbolic cosinus of beta to the power en. Now, as I said, I will first sum in sigma. So we have at the end the sum over a, which are all subsets of en, of the hyperbolic tangent of beta to the power a, well, the number of elements and the number of edges in a. And now I have a sum over all sigma in omega n and a product over all z in lambda n of sigma z to the power dA z. So this is, remember, the degree of z in A, so, or the degree incidence of z in A, which is the number of edges whose z it's one of the vertices, which z it's one of the vertices. So this is the sum, and now what I propose to do is to compute this summation. To compute this summation, let's enumerate all vertices of lambda n, so x1 up to x lambda n. Remember, lambda n has 2n plus 1 to the power 2 elements, so this is an enumeration of lambda n. And so by summing over omega n, what we are doing is that we are summing over sigma x1, which can take the value plus or minus 1. Then we sum over the possible values of sigma x2, which is also plus or minus 1. And we proceed in this way until at the end we sum over sigma x lambda n, which also can take the value either plus 1 or minus 1. So we are summing this expression z in the product z in lambda n of sigma z dA z. So this is what we need to do. So let's start by summing over the possible values of sigma x1. So you see, when I sum over the possible values, here I have a product over all vertices of lambda n. So sigma z, it's fixed for z different from x1. So this product gets out of the sum. And what I get is that, and what I will write here is just this first sum. So this first sum, it's equal to the product for z in lambda n minus x1, sigma z to the power dA z, mind that A is fixed, so we fixed some A, and we are performing this sum. And now I have the sum of sigma x1, which is either -1 or +1, of sigma x1 to dA x1. And this sum here, you see that if dA x1 it's even, so, well, dA x1 can be either 0, 1, 2, 3, or 4. So if dA x1 is 0, 2, or 4, when you take either 1 or -1 to the power an even number, this is 1, and you are summing over 2 possible values of sigma x, so this will be equal to 2. So if dA x1 is even, this sum is equal to 2, while if dA x1 it's odd, then we have here, well, when sigma x1 it's 1, that will give me 1. If it's -1, it will give me -1. So we have 1 minus 1, and this is 0. So this sum will be either 0 or 2. It will be 0 if dA x1 is odd, and 2 if dA x1 is even. So this is equal to 2 times, well, let me, the indicator that dA x1 it's even. Right? This indicator means that, well, this is 1 if dA x1 it's even, and it's 0 otherwise. This happened when we summed over sigma x1. Now I will repeat the same argument by summing over sigma x2. But now, when summing over, so let me replace this expression by, we already summed the first one, and now we have here it's minus x1, and we have 2 times the indicator that dA x1 it's even. And now I'm going to sum over sigma x2. So I will just repeat the same argument, and when summing over sigma x2, I'll say that, well, if z is different from sigma x2, this is fixed, so it gets out from the sum. So I'll have now this sum, we have this factor which gets out. I will not write it. And then here I have, well, in this product, I'll take out the value x2, and I'm summing over sigma x2, which is either plus or minus 1, and I'm summing that sigma x2 to dA of x2. And again, this sum, it's either, by the same reasons, 0 or 2. 0 if dA x2 now it's odd, and 2 if dA x2 it's even. So that will give me now, after summing x2, I'm moving, so what I get now, it's a sum. The first sum will be over sigma x3. Here I have x2. I removed x2. I got an extra factor 2, but now I require that both dA x1 and dA x2 are even. And you see, by summing over all these terms, at the end, what I get is 2 to the power of lambda n, the number of sides, the number of vertices, and, well, for this to be different from 0, I need that all degrees to be even. So what we just proved is that this big sum, it's equal to 2 to the power lambda n, and here I have an indicator that I need dAx to be even for all x in lambda n. So this is a formula for the partition function. I have proved that the partition function is equal to this factor times this factor, And now I have a sum over all subsets of edges of En. These wait for the set A, but I'm summing only over sets of edges A such that the degree of each vertex is even for all x in lambda n. So I can rewrite this partition function as cosinus hyperbolic beta En 2 to the power lambda n. And now I'm summing over all A subset of En such that dAx it's even for all x in lambda n of the tangent, the hyperbolic tangent of beta to the power A. So this is a formula for the partition function of the Gibbs model. And mind that I never used here the fact that beta is large or small. This is always true, but this formula will be useful only in the case in which beta is small. So here is an example of a set A, a subset of edges in which all degrees are even. So you see that because here the point is that what we are requiring is that all degrees in lambda n are even. So you have your set of edges, and so you see that, well, if the vertex is not used, so the degree is 0. So now these are the vertices which are used by A. So this one has an even degree. The degree is equal to 2 because it has 2 edges. This one also, this one also, this one also because it has 2 edges. This one has 4 edges. This one has 2, this one has 2, this one has 2, this one 2, then this one has 2, this one has 2, and this one has 2. And of course, the vertices which are outside lambda n have whole degree 1, but we are not requiring them to have even degree. They can have not degree. So this is an example of a set of edges which is counted in this sum, right? And it's over this type of edges that we are summing. This type of sets of edges in which you are summing. And you can easily convince you that if a set A belongs to this family of subsets of En, you need at least one or two of the edges to belong to the boundary of lambda n. You can't have a subset which is not linked to the outside if and which has all degrees inside lambda n to be even. So this is the formula for the partition function. And now, so we will express this expectation as a numerator divided by the partition function. This is the formula for the partition function. Now I will use the same formula for the weights in order to compute the numerator which appears in this expectation. So what we want to estimate is the expectation of the spin at 0. But this is by definition the sum over all sigma in omega n, sigma 0 times the measure of the configuration, the probability measure of the configuration sigma, but this is exponential minus beta h plus n of sigma divided by the partition function zeta n plus beta. So in the previous take we obtained a formula for that partition function. So now what I want to compute is the sum. To compute or to get a formula for the sum over all sigma in omega n of sigma 0 exponential minus beta h plus n of sigma. And what I will do is that I will use exactly the same expression for the weight in order to simplify this sum. So let's replace this weight by this formula. Let me forget for a while this factor, and as we did before, let's first sum in sigma and then in A. So what I have here, it's a sum over all A in En of the hyperbolic tangent of beta to the power number of edges in A, and then we have a sum for all sigma in omega n. The difference with respect to the partition function is that we have this extra factor sigma 0. So we have here sigma 0 times the product of z in lambda n, sigma z dz of A. And of course, once we have this factor, what we will do is that we'll write this product as a product outside sigma 0, and then what we get is that sigma 0 will appear with its degree plus 1. And here I'm changing notation introduced, sorry. So this is dAz, and this is dA0 plus 1. And now remember that we are summing over all sigma, so we obtained an enumeration of omega n. So let me start my enumeration to simplify by assuming that the first element of my enumeration is 0. So this sum, which is over all sigmas, I will do it as all sigma 0, which is either plus or minus 1, then the sum over all sigma x2, which is plus or minus 1, up to the last one. So here are many sums over the last one, which is over sigma x lambda n. Now, by summing over sigma 0, you see that this is a constant, it gets out from the sum. And now by repeating the same argument, we get that this sum will be either 0 or 2, but now we have a difference that this sum will be 2 if d of A0 is even and 0 otherwise. So d if dA0 is odd. While for all the other ones, we have the inverse. So the sum will be, so this is if z is equal to 0, and if z is different from 0, this sum will give you 2 if dAx or dAz it's even and 0 otherwise. So by summing, and while I don't give you details now because we did it very carefully for to the partition function, so what I claim is that this sum is equal to 2 to the power lambda n, so the number of elements of lambda n. Now we have an indicator, but the indicator is slightly different. The indicator is that we need dA0 to be odd and dAx to be even for all x different from 0, x in lambda n. And mind that by requiring dA0 to be odd, this means that dA0 is either 1 or 3, which means that 0 has to be a vertex used by one edge of A. Right? So the set of edges A contains an edge whose one of the endpoints is the origin, because we are imposing here that dA0 is odd. So this is the formula we get for the numerator. So now we have a formula for the numerator and a formula which I erased for the partition function. So now we can just simplify this expression and get something which does not depend on sigma anymore, so we have now reached the point in which we have a formula for this expectation which does not involve anymore sigma, but only subsets of edges. So before I erase, let me stress one point, is that when I computed the numerator here, mind that I told you that I would not take into account this factor. So actually, you have this factor here, right? The cosinus hyperbolic to the power en. And this factor here, which does not depend on a, as well as this one, they only depend on n, appear in the numerator and also in the denominator, so in the formula for the partition function. So once I rewrite, so I replace the partition function by the formula I obtained, and this sum by this formula, you'll see that these two factors will cancel. So what will remain in the numerator is the sum over all subsets times this tangent hyperbolic of to the power a and this indicator. And in the numerator, I will have a very similar formula, but in which only the indicator is slightly different. So what I will do now is I will erase everything, and I will just keep a formula for this expectation, a formula which does not depend on sigma anymore, and in which these two factors do not appear anymore. So this is the formula we obtained for this expectation. This expectation is equal to this ratio. Here, I'm summing in the numerator, I'm summing over all subsets A of En, the set of edges, such that dAx, so the degree of x at A, it's even for all x in lambda n minus 0, for all x in lambda n different from the origin, and dA0, so the degree of 0 at A, it's odd. While in the denominator, what we are summing the same weight, but for all sets A in En, such that dAx, the degree, are even for all x in lambda n. So now we'll introduce some notation. If I have a finite set, so A, an element of E, so or a subset of edges, I will represent by delta A, so the set of edges which do not have any vertex in common with A. So these are all x, y in E, such that x and y does not belong to V of A. So remember, V of A is the set of vertices, the set of points in Z2, which are used by edges in A. So here we are requiring x and y to form an edge, and that x and y do not belong to A. So let me give you an example. So let's say that here is a set A, a set of edges. Now, delta A, well, delta A does not contain this edge. Does not contain this edge because, well, does not contain this edge because the one endpoint of this edge is this one, which is also an endpoint of an edge in A. This edge does not belong to the delta A because both of its endpoints are also endpoints of an edge in A. But this edge here belongs to delta A. So delta A is just, well, family of edges, so the set of all edges in E whose endpoints are not endpoints of edges in A. So this is a definition. And why do what I'm doing here? Well, let's take A in set in the numerator. So I know that the A of 0, it's odd. This means that 0 belongs to VA. So there is an edge whose in A, whose endpoint is 0. Let me represent by A0 the connected component of 0. So if you have, so let's say that here is the origin, and here is A, so A0 will be just this family of edges. So all edges which belong to the connected component of A, which contains the origin. And let me define by A1. So A1 is the complement. So A1 it's A minus A0. But mind that A1 it's an element of, it's contained in delta of A0. Right? All vertices of A1 are not vertices of A0. Because if one of them were a vertex of, if one of them were a vertex of A0, then this subset will belong to the connected component. So since I defined A0 as the connected component of the origin in A, so the connected component in A of the origin, if delta A1 is the complement of A0, so all the set of edges in A which do not belong to A0, then A1 has to be contained in delta A0. That's fine, because now, with this notation, what do I know? Well, I can, in this sum, I can first sum over all possible subsets. So I'm rewriting this sum. So in this sum, I'm summing over all subsets of edges with these two properties. But now I can define the connected component of the origin. I know that the origin belongs to A, so I can define its connected component, and first fix one connected component. Once you've fixed this connected component, what you're doing is that you're summing over all A1, which is contained in delta A0. And by doing this, I'm counting, so A0 union A1 corresponds exactly to the sets of A contained in En. But what are the properties of A0? Well, the degree in A0 of X has to be, of the origin, has to be odd, right? Because the degree of 0 in A0, it's equal to the degree of 0 in A. Because A0 is the connected component which contains the origin. And the degree in A0 of X is to be even for all X in lambda n minus 0. Because again, since A0 is the connected component, the degree of X in, well, I didn't wrote that as degree, just as D. Sorry for that. So this is dA0, dA0 of X. dA0 of X has to be even because dA0 of X is equal to dA of X, right? Because since A0 is the connected component of the origin and I'm taking a point X, either X does not belong, it's not a vertex of A0, in which case this is 0, or if it is a vertex, then its degree, it's equal to the degree A of X, which is even. So in all these sets, dA0 of the origin is odd, dA0 of X for any other X, it's even. While here, since A1 has no common vertex with A0, Well, the origin does not belong is to the vertex, the set of vertices of A1. So here what we have is that the degree A1 of x is to be odd for all x. It's to be even for all x. Right? So you fix any x, either x, it's not a vertex which appears in A1, in which case it's 0, or it is a vertex which appears in A1. Since A1 has no connection with A0, its degree corresponds to the degree of x in A, and the degree of x in A, it's even, unless x it's in the origin. But the origin does not belong to A, because it belongs to A0. So the origin does not belong to A, so the degree of the origin in A1, it's equal to 0, and in particular it's 0. It's even. So this sum in the numerator, it's equal to this sum, and this sum I can arrange it, well I can, since the number of edges in A, since A it's equal to A1 union A0, the number of edges in A is just the number of edges in A0 plus the number of edges. So I can rewrite that expression as the product of these two. So here in this sum, I'm summing over all subsets A0, which are connected. Such that the degree of 0 in A0 is odd, and all the other degrees are even. So this is the first sum. And in the second sum, I'm summing over all A1, which are contained in delta of A0, and such that the degree of x in A1 is even for all x in lambda n. So for all x in lambda n. So let me repeat this argument to make sure that you understood. I have here a sum over all subsets of En, which have the following property. The degree of 0 in A is odd, and the degree of x for any x in lambda n different from 0, it's even. Since the degree of 0 is odd, this means that 0 belongs to A, and I define A0 as its connected component. So here is A0, say. Here is the origin, here is the connected component of A0. Then I have another family of edges in A, which do not belong to the connected component of A0. I call this family of sets, so A1. And what I'm claiming is that if I want to sum over all such A, so over all A which contained the origin, so let's forget about the degrees. By summing over all set of edges which 0 is a vertex of one of the edges, I can first sum over all possible connected components which contains the origin, and then sum over all sets which do not intersect with this connected component. So this is exactly what I did here. I'm summing over the connected component, which contains the origin, and then with all the other possible sets. But now we are not really summing over all connected components which contain the origin. We need something more. Here we are summing over, we are requiring that the degrees are even for all x and odd for the origin. So what does that mean for this connected component? Well, for this connected component, it means that 0 has to be a degree odd, because the degree of 0 in A0 corresponds to the degree of 0 in A. And then the same thing is true for all the other points x. Because, well, either x, it's a point which does not belong to A0, in which case its degree in A0 it's equal to 0, and in particular it's even, or x, it's an element of A0, it's a vertex which belongs to A0, in which case its degree in A0 it's equal to its degree in A. Since its degree in A has to be even, its degree in A0 has also to be even. So these connected components need further properties. dA0 needs to be odd, and dA0 x needs to be even for all x in lambda n minus 0. And the same argument applies here. Here we are summing over all A1 which do not intersect A0. And since we are requiring here all the degrees to be even, and since the origin does not belong to A1, this means that we have to sum here over all sets A1 whose, with the property that the degree, again, d of A1x, it's even for all x in lambda n. We can include the origin because anyway the origin does not belong to A1. So I hope you're convinced that this formula holds, and which means that this expectation it's equal to the sum, which I rewrote in this way, divided by this one. But now if you compare this second sum with this one, you realize that the sum over all A1, so A0 it's fixed, here you're summing over all subsets A1 in En of En with a certain property with the same weight as before. So all terms in this sum, since we are requiring the degrees to be even for all x, all the A1s, the sets A1s which appear here, also appear here. The weights are appearing in this sum are exactly the weights appearing in this sum. So you realize that the ratio of this sum divided by that one, it's bounded by 1, which means at the end that what we have is that the expectation of sigma 0 with respect to the Gibbs measure and beta with positive boundary conditions, it's bounded by the sum over all A which are connected and such that the degree of 0 it's odd and the degree of x it's even for all x in lambda n minus 0 of the hyperbolic tangent to the power A. So we have proved this bound for this expectation. And is this bound that will show, this expression that will show converge to 0 as n tends to infinity. So we just proved that this expectation it's bounded by this sum. Now we want to estimate this sum. To estimate this sum, I will use the following simple lemma. So let G to be a connected graph and let's assume that this connected graph has n edges. Then what I claim is that for all x in the set of vertices, so let me represent, so maybe G is a graph with V as the set of vertices and E as the set of edges, and we have n edges. So let me take any vertex x, and what I claim is that there exists a path which starts at x and crosses all edges twice. This is the claim. So if you take any connected graph with n edges, you take any vertex in this graph, you can find a path which starts at x and cross all edges twice. So let's see. You have, let's say, this graph, which is a connected graph. It has a certain number of edges. Say that you started from this point, and you want to find a path which crosses all edges twice. So let's say that here, this will be the path. So let me do it again. You started from this point, you go in this direction, you go in this direction. Once you go there, you return. Here, you go there, you return, then you reach. At this point, you cross this edge twice, this one twice, this one twice, and each of these only once. So you can either do a turn or go back of what you did. So you go back and you cross each edges twice. So, well, this proves at least that for this graph, starting from this point, there is such a path. So let's prove this lemma. The proof is by induction. So if there is only one edge, that's very easy. You just, if you start from any of the two vertices, you can define easily this path. Now let's assume that it holds for all graphs with n edges and which are connected. And let's consider the graph Gn plus 1, which is a graph with n plus 1 edge. What I claim is that this graph, let's say the one I draw, I don't remember, no, it wasn't this one. What I claim is that this graph with n plus 1 edge can be obtained from a connected graph with n edges. So what I claim is that this graph which is connected and has n plus 1 edge can be obtained by adding an edge to a graph with n edges. So you see, it's like you start with this graph with n plus 1 edges, and you want to erase one by one edge, but keeping the graph connected. So here it will be very easy. You could, let's say, this means that what you don't want to do is to erase this edge, right? Because if you erase this edge, you get a graph which is not connected anymore. But what I claim, and I won't prove, but because the formal proof will take some time, well, what I claim is that I want to convince you that this is possible. So in this example, you could erase, let's say, first this edge. You still have a connected graph, then this one, maybe this one, this one, this one, this one, and at the end. So what I claim is that in this construction, you can, if you have a graph with n plus 1 edges which is connected, you can write it as an edge union a graph. So this one, it's connected, and these edges which you're adding to the set of edges. So let's say that what I mean by here is that in the set of edges, n plus 1, you're taking the set n and you're adding, and well, maybe Gn plus 1 can be either equal to a set of vertices. Vn plus 1 can be either equal to the old set of vertices, or Vn union a new point z. But so this means that this graph with n plus 1 edges, it's equal to a graph with n edges and you add a new edge which is attached to one of the vertices of Vn. So if you assume that, then now you want to prove the claim, take x in Gn plus 1. So assume that x belongs to Vn. So remember, either Vn plus 1 it's Vn, or Vn plus 1 it's Vn where you add a new vertex. So let's consider the two cases. Let's assume that you started from Vn, and let's say that the new edge E, let me call it yz. And at least one of the two vertices y, they belong to Gn, so let's assume that y belongs to Gn. So this is the new vertex the new edge that you added to the set of edges in order to construct Gn plus 1 from Gn. And let me represent by y and z the endpoints. So you start from Vn, so you know that there exists a path which goes from x to x and which visits each edge of Gn twice. So you take this path, gamma, until you reach y, which is the point in Gn, which is also a vertex of the edge you added. Once you reach y, what you do is that you visit z, and you go back to y. So you visit this edge, which you added twice. Now, once you're back at y, you can continue until you return. So this, what you did, is you took the original path gamma. This path visits all edges twice, and you constructed a path which also visits the new edge yz twice. So let me repeat the construction. I want to prove that starting from any vertex of Vn plus 1, I can construct a path which visits all edges twice. So let's first assume that x belongs to Vn. If x belongs to Vn, there is a path which goes from x to x and visits all edges twice. Since y belongs to Vn, it appears at some point in this path. The edge yz does not belong to the graph Gn plus 1 because this is the edge you added in order to get yz does not belong to Gn because this is the edge you added to Gn in order to get the graph Gn plus 1. So here is the edge. So the path you construct is the path which goes like the original path up to the first time you reach y. At this point, you visit the edge yz, back and forth, and then you continue by the old path gamma, and in this way you get a path in Gn plus 1, which starts from x and visits all edges twice. Now, assume that x does not belong to Vn. So in our example, x is equal to z. So y belongs to Vn, but z does not belong. Well, but starting from y, by the induction assumption, you know that there exists a path which visits all edges of Gn twice. So this is the path gamma. And now you want to construct a path which starts from z. So what you do is you start from z, you go to y, you now follow the path gamma until you return to y. This path visited all edges twice, and now you go back to z and you have the path. So that proves a dilemma. So it's always possible to, for any point, any vertex, it's always possible to construct a path which crosses all edges of the graph twice, if the graph is connected and finite. So let's go back to the proof, and remember that we are summing over all sets of edges which are connected, which contain the origin and which have this property. What I claim is that the set of vertices of A must contain an element which does not belong to lambda n. So the set of vertices of A must contain an element which is not in lambda n, because we are requiring d of 0 to be odd and d of x to be even. Why is that so? Well, take a set of edges, which is finite. Now, count dbx for all x in Z2, but this sum it's finite because, well, the number of edges it's finite. So dbx is 0 for all x but a finite number. So what's happening here is that if you see that if you fix an edge, each edge has two vertices. So if you're counting the degree of each vertex. But since each edge has, so if I count this edge, I'm counting, this gives me a contribution equal to 2. Then if I count this edge, so I'm fixing B, and I'm counting the degree of each x, and I'm summing over all x. But I want to count this total number of degrees by fixing each edge of B. And each time I get an edge of B, for this total sum, I have a contribution of 2. So what I claim is that this is actually equal to 2 times the number of edges, because each edge of B, and this is the total number of edges, has 2 vertices. So if now I'm counting the degree of each vertex and I'm summing that over all vertex, I will get exactly equal to 2 times the number of edges, because each edge has 2 vertices. And so by, say, counting the degree of this whose total contribution is 2, well, it's 2 because I'm counting the contribution of this vertex, which gives me 1 for each endpoint, and I'm counting this edge, which gives a further contribution of 1 for this. So what I claim is that this identity holds. Formally, you can prove it by induction on the size of B. I leave it to you as an exercise to prove that this identity holds. But what's important here is that, well, this sum, it's always an even number. And since dAx, it's even for all x in lambda n different from 0, and dA0, it's odd, the sum here, what I get, is that the sum for all x in lambda n of dAx, it's even, it's odd, I'm sorry, but I know that the sum over all x in Z2 of dAx, it's even by this result, which means that there exists x which is not in lambda n, for which dAx it's larger or equal than 1, and therefore A must contain a vertex which is not in lambda n. So this means exactly what the claim I wrote here, so that the vertices of A must contain an element which is not in lambda n. So now I want to estimate this sum, and the way in which I will estimate, well, I will fix the size of A, and I will sum first over the size and then over all possible connected components of a fixed size. So what I want to do is I sum over all k, say larger than 1. I have here the hyperbolic tangent of A. And now here, what I'm doing is that I adding a further condition in this, for this set A. A, it's a subset of edges. It's connected. dA0, it's odd. dAx, it's even. And now I'm saying that total number of elements of edges of A is equal to k. And so here, I'm sorry, I have to write this as k. And what I need to do is to estimate this number. The first thing I observe is that since A contains the origin, it's connected, and we have seen that it contains also an element which is outside, well, we need at least n edges. So the number of edges cannot be smaller than n. So this sum, I can start it from n. Then a second object is that, well, the hyperbolic tangent of beta, it's bounded by beta. So I can bound this expression by beta to the power k, by using just the fact that the hyperbolic tangent of beta is bounded by beta. Now I need to count this number of subsets. So I want to count the number of subsets which contain the origin and which have k edges. Well, given such a subset, I can map this subset of edges to a path by the previous lemma, to a path gamma, which starts from the origin. So I know that A, it's connected, it has k edges, so there exists a path of size 2k which starts from the origin and ends at the origin. And of course, if I have two different sets, so if A is different from A prime, the path obtained from A, well, there are many paths, but all these paths are different from the paths obtained from A prime, because, well, the number of edges, the set of edges of A prime is different from the set of edges of A. So whichever path going from 0 to 0 and passing by all edges twice will be different from the path which starts from 0, ends at 0, and cross all edges of A prime twice, just because the edges of A prime are different from the edges of A. So whichever path I choose, gamma 0 for A, or gamma, let's call that gamma A, whichever path I choose, gamma A, this path will be different from the path gamma A prime. So the total number of sets, it's bounded by the total number of paths starting from the origin, ending at the origin, and with size 2k. And how many such paths do we have? Well, starting from the origin, we have 4 possible choices for the first jump. So there are 4 possible jumps. Once we jumped, then at this point we have only 3 possibilities. And since the path has length 2k, this tells me that the total number of paths of size 2k starting from the origin and ending at the origin is bounded by 4 times 3 to the power 2k minus 1, and that I will bound just by 4 to the 2k. So this is a bound for the total number of paths, and therefore this sum, it's bounded by 4 to 2k. And therefore, this sum, it's bounded by sum for k larger than n of here I have 16 beta to the power k. And what I see is that if beta is bounded by 1 over 16, as n tends to infinity, this expression converges to 0. And this completes the proof of the theorem. We just proved that this limit sup is less or equal than 0, provided beta is bounded by 1 over 16, because, well, this is summable if beta is bounded by 1 over 16, and therefore, as n tends to infinity, this expression converges to 0. And this completes the proof of the theorem. So we proved this theorem, and now I want to show you that the expectation with positive boundary conditions, it's always positive. And that will show that indeed the limit is equal to 0. And this is telling you that, well, if you place plus boundary conditions, then the probability to have a +1 spin, it's larger than the probability that the spin is -1. So this is a particular case of the so-called GKS inequalities. And I will give you reference in the notes for these inequalities and for the proofs of these inequalities. So, well, this is a particular case. So let's write what is sigma 0 plus n beta. So this is 1 divided by n plus beta, the partition function, and then a sum over all sigma in omega n of sigma 0 exponential minus beta h plus n of sigma. Well, we want to prove that this is positive. The denominator is certainly positive. So what we need to prove is that this expression is positive. Let's go to this expression. So we have here sum in sigma in omega n, sigma 0. And now let's remember the value of the exponential. So this is exponential beta over all sum x, y in En, sigma x, sigma y, with the convention that sigma x is equal to 1 if x does not belong to lambda n. And I can rewrite this just as a product. So this is sigma in omega n, sigma 0, and here let me write that as the product xy in En of exponential beta sigma x sigma y. Now we will use the fact, we will write this exponential as a sum. So this is sum, sigma 0, product, and here I will write n larger than 0, 1 n factorial beta x y to the power n. I'm just replacing the exponential by the sum of this object to the power n divided by 1 over n factorial. And mind that we have a product. So for each bond xy, we have a sum. So actually we have this sum multiplied by another sum, multiplied by another sum. And so what I do, it's, since I'm doing this product, instead of summing over n, I will sum, well, this value, so this variable, I will write this variable as nxy greater than 0, right? nxy, so I'm replacing this nxy, and since I have a product, so what I will get is that I have nxy, and here one product over all x, y. So this is a sum over all nxy, right? So over all bonds, xy in En of 1 over n xy factorial beta sigma x sigma y to the power n xy. And therefore, this sum, it's equal to the sum over all sigma in omega n, sigma 0, then a sum. But here you have to remember, if what I mean here is that, let's say that I'm enumerating all edges of En. So let's say that En, it's equal to this edge E1, E2, until the edge En. So this sum here, it's indeed a sum of En1 larger than 1, and E2 larger than 0, up to En. So maybe to make it more understandable, let's see that here I'm doing eta E1 larger than 0, eta E2 larger than 0, just to n, not eta, n E1 larger than 0, n E2 larger than 0, n En larger than 0. And where E1, E2, En is an enumeration of all edges of En. And for each edge in En, I'm taking 1 over n factorial, which is this variable, b sigma x sigma y, to this product. So what I can do, as I usually do, is to invert this sum. So here I have a sum over eta E1 larger than 0, eta En larger than 0, then the sum for sigma in omega n, sigma 0 times the product of x, y in En, one over eta x, y factorial beta sigma x sigma y to the power eta x y. Fine, so you see that this expression here does not depend on sigma, so it can get out, so I can replace this, I can take it out. So this is, let's say, all Ej of 1 over n Ej factorial, and then I have a sum for all sigma in omega n, sigma 0 times this object. So beta can get out also. So let me take beta. So beta is a sum over all n Ej. And here I have a sum over sigma in omega n. So this is what we get. And now what I want to, my point here is that this sum will be by the same argument as I used before. So this sum, sigma 1 up to sigma in lambda n, I can divide it as a sum of sigma x1 equal to plus or minus 1 up to sigma x lambda n equal to plus or minus 1. And mind that these exponentials are fixed. They are numbers, non-negative integer numbers. So when I do this sum, I proceed as before. So let's say that I will start summing at sigma x1. So all the other ones are fixed. What I will get from by summing in x1 will be that this is either 2 or 0, depending on the value of n xy. Then I will sum on sigma x2, and summing on sigma x2, I again will get either 2 or 0. And by repeating this sum, at the end, I will get either 2 to the power lambda n if certain conditions on n are satisfied, or 0 if these conditions are not satisfied. But my point is, this is always non-negative. So this sum here will give me a non-negative contribution. And all the other terms are non-negative. So this sum will be certainly non-negative. So let me make my point again. So we rearranged these terms, and at the end, I had to compute this sum. But by repeating the arguments we used in this lecture, we reached the conclusion that this sum, it's always either 2. Well, when I sum over only one spin, this sum, it's always a term times either 2 or 0, which means that by performing the sum over all sigmas, at the end, I will get either 2 to the power lambda n if certain conditions are satisfied by these powers, or 0 if these conditions are not satisfied. But in any case, this expression will be non-negative, which means that this sum is non-negative. Since these terms which appear here are also non-negative, what I get is that indeed the numerator is non-negative, and therefore this expectation is non-negative. So this proves this very particular case of the GKS inequality, which tells me that with boundary conditions this expectation is non-negative, and that proves that indeed if beta is smaller than 1/16, this limit of this expectation is equal to 0, which means that the probability that the spin is equal to -1 when we have plus boundary conditions converge to 1/2, showing that the origin is not affected by the boundary conditions if beta is small, which means that if the temperature is very high. And therefore, this shows that in 2 dimensions we have a completely different qualitative behavior at high temperatures and at small temperatures. At large temperatures, what you see is that the boundary does not affect locally the origin, while if the temperature is small, if beta is large, these boundary conditions will affect. So there is a phase transition, and this is what I wanted to prove.